this auxiliary addition, which is commutative and which is associative and satisfies the distributive law with respect to the multiplication.
So it is really something which is opposite, right? In a ring, you have the addition, which is a group, and the multiplication.
No, but
is that here you play the other way around.
repeat, please. I mean,
You have an addition, so it is a group with respect to multiplication.
right, like in a field.
Right?
In a field.
No. A field
Is the opposite.
Is a
Because
group,
there is zero. Because there is zero. Okay, right.
Yes.
Now I
Without
understand.
zero.
It's really, yes, it's
Because
twisted,
there is
this
zero.
thing.
Yes. So
Okay.
you don't have the zero element.
You don't have zero.
There is no zero
Okay.
element.
Okay, thanks. Now.
Of course, if you cancel the zero element, you don't have the addition. The addition is no longer defined.
Yes.
Well, what the addition?
It's no longer defined. If you take a field and you cancel
yes.
the zero element, you don't have a semi-field.
Really?
You could play the game of calling addition what is multiplication. But it won't work, I think.
No, because of the distributive law.
Right.
I think another way to say it is that not every semi-field can be embedded in a field.
Yes.
Right.
For example, this one. I don't know if there is a field.
Yes. No, it's because we're used to one structure, we try to see what is the correct, how it relates, but it doesn't, so it's...
Yes, there is this example of the positive integers, positive real numbers, which are semi-field. But for the rest, I don't know in general. But in any case, this is our example that we want to consider. And don't remember if I gave you also the definition of cluster algebra of geometric type.
No.
Maybe not. So the exchange pattern has the cluster algebra is of geometric type. If three conditions apply, one M is normalized. Or maybe one where P is a semi-field. P is the tropical semi-field. A tropical semi-field. Three, that all coefficients P, I, T has positive, has non-negative, non-negative exponents when they are expressed in this form, as elements in the tropical semi-field. Okay. So why do they call this geometric type? The reason is that all cluster algebras come from geometry like this. So they are all,
Grassmannians, for instance.
for example, the Grassmannians. So, and this cluster algebras can be encoded in a matrix.
What's T for the Grassmannian?
What?
No, fammelo dire a me. P for the Grassmannian. Non me lo dire. So P is so the integers won't do it, right?
No.
Because you see, the Grassmannian have the Plucker have only integral coefficients. So it seems that P maybe it's Q plus. for Grassmannian?
No.
No,
Because it must be tropical. That's what.
Yes.
not Q
The
plus.
P, in the case of the Grassmannian, is the tropical semifield generated by cluster variables associated to the edges.
See.
Okay.
You need all of those.
Yes.
Because, no, wait. No, sono confusa.
In the definition, we never used the addition.
No, but there will be, wouldn't they be inside the Q? No, it's not rational. It's not the positive rationals, no. There will be this coefficient for the Grassmannian.
The positive rationals.
P.
P. So for
Because you need the extra variables.
yeah, so the coefficients were generated by the variables
Ah.
on the edges.
Okay.
Maybe we
Ah.
also need to add some numerical coefficients.
Right. But the variables, so you need this. So when you say the free abelian group, it actually will have letters.
But-
It's not.
Say if you consider integer coefficients, the tropical semifield is generated by the edges, by the variables associated to the edges, and one.
And one.
Okay.
No, but what I'm trying to say is the
You are-
example R plus is very deceiving. Because
Yes.
in the geometric examples, it will be some Z, it will be the quotient field of Z x1 xn, right? That's what P will be.
No, I don't think so.
No, I think so. So like, what is P for the Grassmannian? So it is
P?
the quotient field,
No, P is not a quotient.
It is a group.
the positive
Because
P is a
factor.
group.
you see addition.
No,
is
I
P is a group.
I am
That's
aware.
strange. It's a tropical semifield.
No, but I'm aware it's not a field. I'm saying it's the semi-field associated.
Generated by 1, x
Right.
2, x 3,
Right,
x and 1.
right.
So
Where
there's this
addition?
n plus 1.
So there is no inverse.
Where do we use addition? We use addition just to say that the sum of the two coefficients appearing in an exchange relation is 1. Okay? So what does it mean
So when
Then
you
the-
write
the-
free abelian group, you mean under
You-
multiplication.
under multiplication? Yes.
Okay.
So it's not the polynomial ring over those, no. It's not
No,
the Z
no, no, no.
x1, 2, x2, 3.
It's a
no.
product of these elements.
But
monomials.
polynomial rings will have the.
Yeah, no, but it's just products.
And addition
And
defined
addition
in that
is-
strange way.
The addition is defined this way.
Why don't they take something which is more familiar, like the polynomial ring over those? Because monomials will be in there, right?
Yes, but we want them to be monomials.
We just want
If
monomials.
you require them to be polynomials,
Everything is
they are polynomials.
inside.
If you want them to be monomials, you may ask this by saying that they are elements in P.
Yes, yes.
The fact that the M is normalized means that the two coefficients appearing in exchange relations
Not the
are
divide.
relatively prime with
Yes,
respect
not,
to
yes,
this
yes.
semifield
I wonder
structure.
why it seems an extra
Thank you.
complication, ma l'abbiamo già detto, io already said that before.
Okay. Yes. Okay, right now we want to encode an exchange pattern of geometric type in a matrix, as we did for the exponents.
So it will be the matrix that we know with some extra condition, right?
We know a matrix for the exponents of the cluster variables. Now we are looking at the exponents of the coefficients.
So we,
Well, of course, it will be similar.
no, unlike the B, we already have which is the
Yes, we already have the B. And now we,
and now we look at another matrix for the coefficient.
Yes,
So it will be a pair. Then our cluster will be given by a pair.
the pair of matrices.
I mean a family of pairs, of course. This is the AU.
Yes, but we want to show that they are all determined by just one matrix. As for the exponents, because then we have the mutation
Right.
rule.
At the-
And we want to show that the mutation rule is the same also for the coefficients. Actually.
Mm.
But well, this is what I want to.
Well, this is kind of obvious because isn't that when we're doing the mutation, somehow wasn't that built, we were taking coefficient equal to 1 at that time? No.
Yeah.
Ah.
Yes, if you want. Yes.
No, but
We
we
were
were
just
not
looking at
assuming
the,
that, right?
at the cluster values. So this was equivalent to looking at to taking coefficients equal to 1.
Ah,
Yes.
because if we were not taking coefficient equal to 1, it would be like embedded into that argument somehow, right?
I believe that one could do a unique argument for the
Right,
utilities.
that's what I'm saying.
That's
But they don't
possible.
do that, they separate them.
They separate. They
Okay,
consider
then maybe it's
first
necessary, okay.
the exponents and now the coefficients. So. So the proposition is that a family of elements BJT on the tropical semifield P gives rise to an exchange pattern of geometric type if and only if there is a matrix that we call CT whose rows are indexed by iota, which is the index set in generating set of the tropical field, and J, which goes from 1 to n. This matrix, iota here and J. When? Where PJT is the product of C iota J positive of P iota C iota J. And of course, this family of matrices must satisfy a mutation rule, which corresponds to our mutation in the graph T. So we write where if T and T prime are joined by an edge labeled J, we call C the matrix CT and C prime the matrix CT prime. Then the mutation is the following: C iota J prime is minus C iota J no, maybe I should use another index here, because J is the fixed index here, so maybe describe if I equals J and it's C iota I plus by
If I
C.
equal iota,
I
yeah,
equals
defines C
J.
prime. Ah, J, that
J,
that J.
which is
Okay.
the index.
Okay.
Iota cannot be equal to
Sorry.
I, they are in two
Una
different
domanda
sets.
io, Solo domanda, dopo che ho finito.
Yes,
Ah,
just-
right, because, okay, sorry.
Mi faccio una domanda.
Maybe I complete this definition. So here C iota J B J I plus C iota J B J I. Well, I write otherwise.
Posso?
Yes.
So I have a question that denotes the absence of study, because I forgot what we proved about the matrix for the monomials.
Yes.
So certainly there is this cluster algebra corresponds to a family of such matrices, right? This is clear. Then we prove that it's not enough that we pick one matrix which is skew symmetrizable and we apply the mutation, because this will not give us in general the whole cluster like
If it
that.
is skew symmetrizable, it will give us in general a cluster
No,
aspect.
but
But
we
if
have
it
the
is
counter-
just sign skew symmetric, it doesn't give us.
Ah, so this is the thing. So if it is sign skew symmetric, we're not sure. But if it is skew symmetrizable, which I forget what it is. No, skew symmetrizable means that
If you multiply
it is-
the rows by
you get a skew symmetric matrix,
Yes.
so by some thing. Ah, that is enough. So really, if we have such a matrix, we can generate the
cluster
whole,
algebra,
yes. But then, what I'm trying to say is that what you said, it doesn't look right to me when you say, oh, it's enough we have one such matrix. No. You may need the whole family, right? Or it is an if and only if. What I'm trying to say is that
for the
this-
coefficients. Or
no, the monomials, like,
For the monomials, if you have one skew symmetrizable matrix, that's enough.
this is clear. But what I'm saying is that could it happen that you don't have a skew symmetrizable matrix so that you really need the whole family of them?
Yes.
Then it's
I
not.
showed you an example.
In fact, then your claim confused me, because it is like I say, in general you need a family of matrices, you don't need just one matrix.
Yes.
Okay,
Yes.
I'm happy. No, because you said we need one matrix and we're happy. Did I get it wrong?
In this case, for the coefficients, you mean, or for
No, not for coefficient.
for the exponents? Yeah, it's in general it's not. true.
Unfortunately, not one. We need the family in general, unless we're lucky that we get this skew symmetrizable and we
If
can.
one of them is skew symmetrizable, then they are all
We're
skew
fine,
symmetrizable.
right, we're fine. Here instead we need one.
Here instead we need one. Yes.
Yes, so it's not how I said it, it's more complicated, you cannot play the same games. Okay, I'm happy.
There are no restrictions then on the structure of the matrix. They just have to have. It just
It's easier.
must have just integer entries. That's, then we apply the mutation. And the rule of the mutation is the same as for the exponents. It looks the same.
No, solo te iota e I in the same form. Only you can do this. No, vabbè, prendo atto.
I use K for.
No, I'm using K, so it's I'm fine.
They look very different.
Eh?
They look very different.
I confess that every time I was trying to write iota, I put
Me too.
the dot over, and then I decided, okay, I had to
Now, the reason is
concentrate
that they say they write I instead of
Guarda
iota.
come l'hai ridotta, le fate prendere gli occhiali, guarda.
But you really get confused if you use the Latin letters. Or maybe I could choose another letter.
No, wait a moment, wait a moment, I'm curious. why are we using a different letter? Because there is a different meaning of that index?
Yes, because
Ah.
the second index is an element from 1 to n,
Ah,
while iota is an element in the index set of the generating set of the tropical semifield.
so it's
So it
not a
must be
square,
different.
it's
It
not
might be
square
bigger, it might be
matrix.
empty. And
No, it's a square matrix.
it's not a
It's
square
not a
matrix,
square
it's a rectangular matrix.
So the other one was square, right?
That one was
That's
square.
very different. No, I call it alpha.
Alpha is a good letter.
Ci vuole poco, perché anche ci voleva.
The reason is that in my notes I have k instead of I, but that in the proof I used I, so I will get confused.
No, no, go on like
Quindi, cioè, in your notes, not to get confused, you have the right, okay.
Yes. Oh, I need this. This is what I need. Okay.
But this is
Proof.
a bit confusing, right? Because isn't that the Bij is 0 on the diagonal, no? I'm confused.
Bij is 0 on the diagonal, yes.
It's a question. Is it true?
Yes.
Then why do you have two cases?
These are.
No, I mean,
Don't see the question.
no.
I mean, BII is 0, but
Yeah,
in
why
this case, BI.
No, because there is the minus sign.
Oh, there is
Okay.
a minus sign, yes. That's,
Okay. Because otherwise it's
otherwise, for I equal J, this is 0.
it's
Yes,
zero, right?
Yes.
Okay, no, but there is the minus. I didn't see. Okay.
Okay,
bet
we could
they-
write it in a unique
I
form.
bet that they don't have-
minus 1, 2.
They don't have two cases, do they? In your paper. They
They
one
have
case.
two cases.
They have two cases. Interesting, because there is a plus or minus. Okay. So it is 0 on the diagonal.
So I will try to do the two parts of the proof at the same time, so both the if and the only if parts.
Scusa, non mi strangola, porta pazienza. No, non ho capito. La B c'ha B has 0 on the diagonals, because here in the examples you put a 0, but then I write,
B is sign symmetric, so it has zeros on the diagonal. Yes.
but sign symmetric has said only that Bij is opposite sign between Bji, but it
Yes.
doesn't say anything about diagonal. But
Opposite
it's
sign for all I and J.
for all I and J, okay. No, vabbè.
In particular, the opposite
No,
of
it's
0
important.
is 0, and the
No,
opposite of
va
plus is
bene,
0.
ma it's a matter of definition, okay?
Yes.
Happy.
So, we start with a family of elements in the tropical semifield with non-negative exponents. And I consider the quotient UJT PJT over PJ prime. We are always in this situation where T and T prime are joined by an edge labeled with J. Which is equal by definition the product of the I got iota figlio T of course this is no this is
No,
for-
factor.
sorry.
Right, you don't know.
So first of all, C iota j t equal to minus C iota j of t prime. This is clear by definition. Because if we consider u j of t prime, then we have the inverse of these elements, and so this.
Yes.
Okay, it's just sorry. It's just a matter of notation. So you are calling pjt and p iota. The pjt are polynomials
These are
in the
models.
variables
P
iota.
Yes, because those
Okay.
are
Right.
no, because the
Okay.
PJs are the ones that from each vertex, right? They correspond.
Yes, this is a product of elements of
P iota are the elements of P, the abelian group.
Okay.
Yes.
This is a notation we used all along, right? Somehow.
Yes.
PJs.
But you just introduced the notation of the PI.
No,
of
it's
the,
true, but
of these generators of the coefficient group. So maybe it was better to use another letter than
No,
P.
it's,
I just changed the index.
but because the P
Make
form
it
and the
appear
PT,
different.
so it makes sense to use P, right? It's the same.
Yes. So let's see. Then the fact that pjt plus pj t prime is 1, this is equivalent to pjt is the product of the iota where c iota j is positive of p iota c iota. Okay, so this means that these two monomials are relatively prime, and so that when we consider the quotient, the positive exponents come from pjt and the negative exponents come from pjt prime. It's the same reasoning as for the variables that we made 2 lectures ago. So the only important thing to show is that this propagation of the elements u I t prime is equivalent to the mutation on the exponents.
No, I don't understand. Is P JT as positive exponent? No, I don't understand this argument. So it's the same argument as, but we forgot all of the arguments, so can you repeat? I think we forgot.
So if this element here is the quotient pjt
Yes.
divided by pjt prime, and these two
See,
elements have no
Yes.
p iota in common,
right.
then pjt
Is all
is
the
the
positive.
product of p iota
I see all the
and these
no,
elements
no,
are-
okay, now I understand. So it's really the same as CIJ, okay, C of J. No.
Okay.
And the other for all the negative.
Yes. So now let's look at this equality and see what does it imply for the exponents c iota I. So you look at the exponent of p iota in these two elements. Here we have u I t prime, so the exponents of p iota is c iota I. Yes. C iota I prime, because we have T prime. Here. I, J. So this is the exponents of p iota in this monomial. Okay. Then this is equal to the exponents of p iota here is c iota I times, it becomes plus the exponents, and this is c iota j times the maximum between b j I j of t, and then here
Plus.
plus yes. So I write here the exponent of this element, and then we comment. And this is the minimum between 0 and c iota j times b j
Minus the ji.
minus, yes. So of course the minus bji is this exponent here. So we have to show that p iota appears with the exponent, the minimum between 0 and c iota j in this element. But this is clear, this is just a definition. Okay? The definition of our auxiliary addition with particle field. And so now we just have to look at all possible cases of B, J, and C iota J.
Non ho capito perché, scusa, quando when I equal j, right? So bij becomes 0. And right?
So this is
So it seems there is some missing coefficient, right?
this is not valid for I equal J.
Ah, okay, because then, okay. We're doing that, this is, yeah, this is done already, okay.
Yes. This is
Okay.
the propagation of the elements U,
No,
I,
no.
T prime.
Okay, okay.
But U, J, T prime is just the inverse of U, J, T. So it's U, J, T to the minus 1. So this is the non-trivial relation, which holds for I different from J. So also this holds for I different from J. Now we have to do some cases. If C iota J is positive and B, J, I is negative, then we have that C prime iota I is C iota I. Let's see. So this is negative, so this disappears. This is also 0. So let's see if this is the same that we have here. If one is positive and the other is negative, these two elements cancel. So we actually have to just C iota I. Then look at C iota J negative and B, J, B, J, I positive.
No, why do they, no, wait.
In this case, these two elements are both 0.
Okay, yes, okay. No, they don't cancel, they're both at zero, okay.
Here they're both 0, and here they cancel.
Ah, they cancel, okay. No, because I heard they cancel, but they're both at zero, so it was not.
Here what do we have? C iota I is C iota I plus C iota J times Bji minus the minimum of 0 and C iota J is C iota J Bji. So they cancel, and also here they cancel because they have opposite sign. Then let's see this one of the two cases. Cij positive and Bji also positive. In this case we have C prime iota I equal C iota I plus, this is positive, C iota J B J I, and this is 0. So in the case where they are both positive, we actually have C iota J B Ji 2 times divided by 2. So this element, and finally C iota J negative and Bji also negative. Here we have C iota I plus, so this is 0, this is negative, so this nothing is 0. So we have minus C iota J Bji, which is this. So in this case they are both negative.
Yes.
So the product is positive with this minus sign, which comes from the negative sign either of this or of this. So it was just a different way to express this, the same rule. Okay, I hope it is clear. In any case, what we have is that the matrix CT changes mutes along the 3Tn in the same way as the matrix BT mutes. So it is natural to consider these two matrices at the same time. Forming a complete matrix B tilde T.
So this concludes the proof, but the other way we have not proven, right? You proved one way only. The other one is the same.
I proved actually both ways. So I proved that
This
this.
is the characterization somehow.
Yeah, I proved that. I mean, that this mutation rule is the same as this, which was what we had to.
Well,
to
you
verify.
prove that both if you make the claim that we already know that the UJT tell me everything. I mean,
Yes.
you have to call that the result. Please.
But we already know that.
No, I know, but you haven't said it. It helps. No, you see, I mean, the things you've said prove one way. If you add this extra information, you prove the other way. But without that information, you don't.
Yeah, I probably say that at the beginning, but okay.
No, you see
Yes.
what I mean?
Yes.
Because that is only one way. The other way needs the information about the UJ holding everything.
Okay.
No,
Yes.
no, I say because I am a slow person that doesn't understand if people don't tell me everything.
No. It's not probably.
Oh, se c'è quello lento.
So we want to put these two matrices together, forming the matrix BT dot T. In this way. So the column index is the same. Is the integers from 1 to n. Then the row index set is from 1 to n up to here, and then we have the
It's not a quotient, it's
Iota.
really the two matrices, right?
yeah, it's a block form.
Block form.
It's a block form.
No, it's block form. Specific.
So the matrix BT is called the principal part of this matrix. BT is the principal part. And of course, if a principal part is skew-symmetrizable, then then we are sure that we can construct a cluster algebra of geometric type for any matrix CT in the denominator. So if we fix, say, if we fix a skew-symmetrizable matrix B0, and we let B0 equal B0 divided by C0, where C0 and C0, then we can construct a cluster algebra of geometric type. This matrix gives rise to.
No, so the mutation applied to C cannot do anything wrong, it will always be the correct pattern.
Yes.
How do we know this? Because you made us nervous with the B, now the C are so harmless. How is it?
The unique condition that we have to verify is that they satisfy the mutation. So there are no other restrictions.
Ah, okay, so it's really.
While the matrix
be
is
anything,
B
okay.
had to be sign symmetric.
Right, this is.
So we have to be sure that when we mute sign symmetric
Okay.
matrix, we have to obtain another sign symmetric matrix. We don't have this condition for C. So the matrix C can be any matrix with integer coefficients. So of course the matrix C0 can be empty.
No, I say this somehow give us the classification of a particular class of them, right? All the ones with the suffix.
Yeah, then you have to understand when two of these are symmetric, are
Equivalent.
isomorphic, as equivalent.
Mm. Isomorphism of cluster.
But we will see many things about the classification
Yes.
soon.
So the three